we improve from Whitler to Cascode? Why we improve from Whitler to Cascode?
In the VDS1
VDS1?
goes to VDS.
VDS1 is here, equals to VDS2, so? So we are improving what?
Voltage.
No. We are improving?
The mirror ratio.
No. For a current mirror, the most important two things is your, one is the output resistance, the other is, no, current mirror. It's a mirror, so the left hand side should be the same as right hand side, I mean ideally lah. Yes, so from a Whitler to Cascode is improve matching. Because the VDS1 equals to VDS2, right? So these pair of current mirror are actually, these pair of transistors are actually perfect current mirror. Because everything for them are the same. So they are perfectly matched. Okay? And this perfectly matched current mirror will force two identical current flowing through these not matched M3 and M4. They are still current mirror, but these two are not matched because their VDS are not the same. But it doesn't matter. The current flowing through them are the same, forced by this M1 and M2. So the whole thing, the whole structure is still considered as a perfect current mirror because their two currents are matched. Okay? So from your simple current mirror to Cascode, it basically improves out and matching. So that's all for your current mirror. You only learn 3 types of current mirror. And now the question is, if you look at current mirror structure, all the structure you draw here, the question is, how you get your IREF? How do you get your IREF? How do you get your IREF?
Put a resistance.
Put a resistor there. Okay. So let's say if we have your simple current mirror. So if you have a simple current mirror, how are you going to generate this IREF? One way is to put a resistor there. And here you connect to a higher potential, let's say VDD. Okay, by putting a resistor there, it's a passive device, right? And because this part is your what? What's the name for this kind of transistor? This kind of transistor is your diode connected transistor, right? And diode connected transistor is basically like a diode, right? So if you look at this side, it's basically VDD, connect to a resistor R, connect to a diode, and connect to the ground. So there will be a current flowing through this branch. When there is a current flowing through this branch, basically it's generating your RF. Because there is a current flowing through. This one is passive, this one is forward bias. And once I apply the voltage difference across these two components, there will be a current flow. And this current is your IREF. And this current can be controlled by this R, right? By this R value. Okay? So that's the simplest way to generate this IREF. But what's the problem? What's the problem about this kind of a method?
very sensitive to changes in power supply.
Yes. What's the meaning of very sensitive to changes of power supply? Which parameter is very sensitive to the change of power supply? Change of VDD? RF. So, okay. So, let's say I know this voltage is delta V. Okay. So, how to calculate your RF?
VDD minus
VDD minus
delta V
delta V
over
over R. Okay, so if we are using resistor to generate IREF, and the IREF will be kind of like this, right? What's delta V? Delta V is basically your what?
VGS.
It's a VGS, right? Here is your delta V. It's basically a VDS of your M1. VDS of M1 equals to VGS of M1, right? Okay, so here is basically VGS. So if you look at this equation, your IREF is proportional to this VDD, right? That means what? That means once your VDD increase, once your VDD got a peak, got a glitch, fluctuate, your IREF will fluctuate accordingly, right? Your IREF will follow your VDD. So your IREF will change, which is undesirable because we want this IREF to be stable, right? Okay, so using a resistor as the reference generator is not a good idea. So how we improve? Any other method? So the first one is to use a resistor. Any other method to generate this IREF?
MOSFET.
MOSFET. How to use MOSFET?
Just replace it with the R.
Okay, another method is actually by using MOSFET. By using one or two, it depends. You can use two, you can use one, it doesn't matter. Example given by your notes is by using one or two. Okay.
No one will have. Good break.
So the example given by your notes is by using two. You can use one as well, as long as you follow its idea. So what's the idea here? Why I can replace the one resistor by this whole bulk? They're actually the same. So what's the idea here? If you look at the rest of the circuit, they're actually the same, right? Just a simple current mirror. This part and this part are the same, right? A simple current mirror. So why I can replace your resistor R by this whole bulk?
Is the EC equivalent?
No.
Gives the same resistance.
Again?
Gives the same resistance.
No, it doesn't matter whether we are just talking about the method. We are not talking about whether their resistance are the same. My question is, this method and this method are actually the same method. Why? This whole block is actually function as a resistor as well. Why? If you look at the transistor connection, these two transistors are your
C.
This two transistor is your what? No? You must be very sensitive to this kind of connection. Now, once you see this kind of connection, you should be able to identify it immediately. This two transistor is your This two transistor is your diode connected transistors, right? What's your diode connected transistor? Is the gate connect to the drain, right? You look at the two transistors, their gate are connect to the drain. This transistor, the gate is connect to the drain. This transistor, the gate is connect to the drain. So these two transistors are actually the diode connected transistors. So if you are going to draw it out, it actually looks like this. It's just two diodes in series. Then connect to the current mirror. And here is a VDD. So this whole part is actually like an R. This whole part are actually like an R. So these two methods are actually the same. So what's the disadvantage for this kind of connection? Disadvantage?
You need to have more of the transistor.
It doesn't matter. Transistor is always smaller than your resistor. And cheaper than your resistor. Because these two methods are actually the same, the disadvantage are actually the same as well, right? The current generated in this branch will actually be sensitive to a VDD as well.
So both are sensitive to VDD changes.
Yes. Once your VDD change, your IREF will change. So these two methods are not very smart. So they improve. So they improve it to what's the better method to generate your IREF?
Can you control the VDD?
Okay?
The second one, you can control the VDD better.
No. It's the same as the first one. It's just by using resistor, the area of resistor is bigger. The area of transistor is smaller. So by having a smaller area, basically you are saving the cost. That's all. But in terms of IREF versus VDD, the sensitivity is still the same. It's still sensitive to VDD. So how to improve this insensitivity? How can I make my IREF stable no matter how my VDD change? Cascode? No.
The Whitla thing.
The Whitla. What's the Whitla thing?
Whitla current source.
What's the Whitla thing? It's actually not the Whitla thing. Your notes is a bit, I don't know, it's a bit confusing, but can I erase these two? It's actually inside the notes. So how we actually generate current, generate reference current is actually by using So how we generate reference current is actually by using this kind of structure. It's a basic structure for the circuit as well. It's a fixed basic structure. It's like your source degenerated transistor. If you still remember, transistor plus one resistor connect to its source. That's called your source degenerated transistor, right? MOSFET. Okay, so this one is also a fixed structure, which is there an official name for this kind of structure? Anyway, you just call it VBE bias. So if you're using BJT, it's VBE bias. If you're using MOSFET, it could be GS bias base. So if you're using BJT, it's a VBE base current generator. So why it is called VBE bias? Because what's the voltage cross this R2? What's the voltage cross this R2?
VBE.
VBE? What? VBE what? VBE?
1.
1. Because here is the base of your Q1, right? Here is the emitter of your Q1, right? So here is your VBE 1. So the voltage cross your R2 is VBE 1. What's the current flowing through your R2? What's the current flowing through your R2? We already know the voltage cross your R2 is VBE 1, right? So what's the current flowing through your R2?
VB1
VBE 1
over
over R2. So this one is the current flowing through this R2. What's the relationship between your R2 and IREF? What's the relationship between your IR2 and IREF?
IREF equals to
IREF equals to?
IREF minus IB1 equals to IR2.
IREF minus IB1, why?
Because got IB1 going the other direction.
Huh?
Got IB1 going the other direction.
IREF is IC, IB or IE? IREF is your IC2, right? It's your Q2's IC.
I see.
So what's the relationship between your IREF and IR2? if you still remember the assumption, if we are using BJT to build current mirror, we can assume what? Unless you are calculating the exact expression for the current mirror ratio. For all other cases, like for example, if you are calculating the output resistance of the current mirror constructed by BJT, okay, for all these cases, we are assuming what? We are assuming beta is very large, right? So IB, beta is very large, so IB is
very small.
It's very small. Why beta very large, IB is very small? Why beta very large, IC can be why beta very large, IB can be very small?
IC 가 IB 오르다.
Again?
IC가 IB 오르다.
IC equals to?
IB 오르다.
Is that correct? IC, IB, IE, which one is the largest?
IE,
Which one is the second largest?
IC,
Okay? So if I'm going to compare IC and IB, which one is bigger?
IC,
IC is bigger. So if I'm going to write IC equation, IC will be equals to beta IB times something or IB divided by something.
beta something.
Okay, so IC is always equals to beta times your IB. So it's not IC equals to beta divided by IB, because your IC is definitely bigger than your IB. So for this case, your IREF is your IC, IC2. So IREF, what's the relationship between IREF and IR2?
IR2 is IE.
IR2 is IE2, yes. And if we assume beta very large, IB very small, then what's the relationship between your IREF and
They are the same.
IR2? They are about the same, right? So IR2 is about your IREF. So that's the expression for your IREF. That's the current you are generating. So that's why this kind of structure is called IB-based current generator. Because if you look at the IREF expression, it is basically IB divided by a resistor. So it's VB. So it's VBE based. So can you find another equation for this RF? One equation I can find is by using this resistor. Can I find another equation for your IREF? So we have equation 1, which is IREF equals to VBE1 divided by your R2. What's the second equation? Can you find a second equation for your IREF? How to find a second equation? Or you can say, how can I rewrite this equation? Because it doesn't make sense. I mean, if you just write VBE1 divided by R2, you are not getting the relationship between your VDD and IREF, right? Now we are talking about how I can improve my reference generator so that my reference current IREF is stable with my it's not going to change with my VDD. So how can I rewrite this equation? such that I can get the relationship between my IRF and VDD?
I can use the diode equation for IC.
The diode equation. What's the diode equation?
IC is equal to
What's the general equation first?
IS exponential
IS exponential
VB over VT.
VBE over
VT.
V
NVT.
VT, right?
VT.
Equals to IC. That's the general equation for your BJT. For your BJT, that's the general equation for BJT IC. In which region?
This one in saturation region.
No.
Or
Forward active, right? Because we are talking about BJT. So for BJT transistor to have this IC equation, this BJT must work in forward active region. Okay, so this is the general equation for IC. So if you look at the Q1, how to write its equation? IC equation, IC1 equals to IS exponential VBE 1 over VT. Okay, so this is the equation for this current, IC1. And how to continue?
You make VBE the subject.
I made VBE the subject.
IC log IC 1 over IS times VT.
Then
this one, wait a second.
Then sub this one into equation 1. Is that correct?
I thought you be using these stuff inside here.
We are finding the relationship between your IREF and VDD, right?
Oh,
So the final equation I want to get is IREF equals to something VDD. Okay, so how to continue? I get the expression for VBE1 already. But if you look at this equation, there is still no VDD, right? Then, oh.
Let's break up the IC and
How to replace your IC? Because your IIS is a constant, VT is a constant, so you cannot replace, it's just a number. So the only thing you can replace is the IC1. How can you replace your IC1 with something contains your VDD?
VDD over
VDD?
R1 over R1
In this case, it's VEE lah, I think. So is?
over R1, V over R1. Oh,
Why? We already assume all the VBs are very small, can be neglected, right? So you don't really need to consider this branch, the VB, the IB. Okay? So how to write your IC? In terms of VE,
VE minus
you tell me what's the current direction in this branch? It's from bottom to the top or from the top to the bottom?
Clockwise direction.
top to the bottom.
Okay, so it's this direction, right? Why?
Orange.
Again? Okay, because minus VE is a negative potential. So if you just look at this branch, here is higher, here is lower, so the current will flow in this direction. Okay, so how to get this current? This current is basically your IC1, right? Because we are neglecting all the IB. So this current is basically your IC1. So how to get your IC1?
VE minus the voltage across the transistor.
VEE minus the voltage across the transistor. What's the voltage across the transistor?
VBE lor.
Huh? How to calculate a current in a branch? That's a basic circuit, right? How to calculate a current in a branch?
IBC.
How to calculate a current in a branch?
Okay, 0 minus
0 minus?
0
Zero
minus VE.
Then? 0 minus minus VE is basically the voltage difference across which 2 points?
Ground
From
and
here to
minus
here, right? Okay. Then how to continue?
over R1 plus.
over
Over what?
R1.
Over R1. Then how to continue? You don't know the resistor for this part. No. You don't know. But if you look at your R1 and this part, they are in series, right? Your R1 and this transistor are in series. Correct? If your R1 and this transistor are in series, that means the current flowing through these components are the same. So that means what? That means once you can find the current flowing through your R1, you know the whole branch current. So how to find the current flowing through your R1? To find a current flowing through a resistor, basically you use your Ohm's law, right? Use the voltage across this resistor divided by the resistance. So how to find the voltage across this resistor? What's the voltage across this resistor?
Minus VEE plus VBE.
Minus VE plus VBE.
Then is the potential
Which
there.
VBE? I got 2 VBE.
VBE 1.
Okay, minus VE plus VBE 1 then.
Then 0 minus that potential over R1.
Why so complicated?
Get the potential there already.